Right. So, let me recapitulate quickly what we already learnt about Möbius transformations, and these were of 4 classes. That is what we had come up to last time. So, Möbius transformations, in which a complex number z goes to W, which is az plus b over cz plus d, and we have agreed that we can always set ad minus bc equal to 1. Now, we classified these transformations into 4 according to the way in which the fixed points behaved. So, we had 2 fixed points and we call them xi 1 and 2, and they were a minus d plus or minus square root of a plus d whole squared minus 4 over 2c, this fashion. Now, when a plus d is plus or minus 2, then of course the 2 fixed points coincide at the point a minus d over 2c, provided c is not 0, and when c is further 0, then you have a linear transformation. So, we found 4 ways of classifying these transformations, and type 1 was so let's write down fixed points, and type 1 had xi 1 to distinct and finite, whereas type 2 had xi 1 equal to xi 2 equal to xi also finite. Type 3 had xi 1 finite, xi 2 went off to infinity, and type 4 had xi 1 equal to xi 2 equal to infinity. Both were at infinity. These are the 4 types that we distinguished. Now, we also introduced the idea of a normal form for all these transformations. In other words, this is not the most convenient way of writing the transformation, but the so called normal form so let me write the fixed point up here. The normal form in this particular case was of the form W minus xi 1 over W minus xi 2 was equal to a multiplier k times z minus xi 1 over z minus xi 2, and k was the multiplier. And this was expressible entirely in terms of the trace of this matrix of coefficients a, b, c, d. So, this was simply equal to t minus square root of t squared minus 4 over t plus square root of t squared minus 4, where t is a plus d. We have used the fact that ad minus bc is 1 everywhere. Okay. The normal form then had this form, and as you could see, you could iterate this any number of times, and all that happens is k becomes k to the power n after n iterations for the nth iterate minus xi 1 over the nth iterate minus xi 2. So, that was extremely convenient to write it in this form. I also pointed out that it was valid even when n was a negative integer. So, you could go backwards and do the inverse transformation and iterate that any number of times, and this would be exactly the same as before, except this would have been raised to negative powers out here. Notice there is a slight sign ambiguity here in some sense. What I call xi 1 and what I call xi 2 is up to me. I have called it according to this. This was xi 1 and that was xi 2, and then k is defined in this fashion, but clearly what you could do is to invert the two, call this the minus sign, call that xi 1, call that xi 2, and then what all that will happen is that k will become 1 over k. So, it is really the pair k and 1 over k that is important, that plays a role independent of choice of which one is xi 1 and which one is xi 2. The normal form in this case was slightly different. As soon as you have the two coincide, it implies that a plus d whole squared is 4 right here, and then the fixed point becomes xi becomes a minus d over 2c, this point here. And then you can also see that if t squared is 4, then k equal to 1 automatically. So the multiplier becomes 1, therefore in this normal form you will not have a multiplier, and what happens now is 1 over w minus xi becomes 1 over z minus xi, right. And then plus or minus c, and plus or minus depends on t is plus or minus 2. So if t is plus 2 you get a plus c, if t is minus 2 you get a minus c. And remember that this xi in this case was equal to a minus d over 2c. So that is the normal form for the second kind, and once again you can iterate it any number of times, and all that will happen is that this c will go on getting added to, it will become n times c after n iterations. Okay. In this case when xi1 is finite, xi2 goes to infinity, this happens when c is 0. When c is 0, this transformation becomes a linear transformation, right, and then there are two fixed points, one of which is at infinity and the other is at some finite value. You can work that value out, we did that last time, and the normal form now is simply z minus xi1 k times w minus xi1 is z minus xi in this fashion, okay. And the multiplier k is a over d. And xi1 is some finite value which you can figure out from this. So this is what the normal form looks like, it is just a linear transformation in this case, plus a multiplier plus a shift. Okay. And finally in this case here what happens is you not only have c equal to 0 but you also have a equal to d, that is the only possibility. And since AD minus BC must be 1, it says a squared is 1 or a is plus or minus 1 as is d. And the normal form in this case simply is w equal to z plus or minus b, and this plus or minus is according as a equal to d equal to plus or minus 1. And this is just a shift, no scaling either, just a shift. So this is what the 4 types of let us call them type if you like. This is 1, this is 2, that is 3 and that is 4. So all Möbius transformations are classified into one of these categories. Okay. Now the great advantage of the normal form is that you can iterate, you can move back and forth, you can compose different Möbius transformations and so on much more easily algebraically than this original form here, okay. But it is entirely equivalent to this form. Okay. Now the question is we saw last time that if you took the most general case, namely 2 distinct fixed points, I solve this for the nth iterate w after n iterations of this, and we got this right hand side to be some Möbius transformation in which k to the power n appeared in the numerator and denominator, and then I argued that if mod k is bigger than 1, then as n tends to infinity all points move towards one of the 2 fixed points, the other one is a repeller, and if k was less than 1 in modulus it was reversed, the roles of these two were reversed, okay. So that helps us see what the role of this multiplier is each time, okay, and that is one more reason why the normal form is of such great significance. Okay. Now the whole of all of this is guided by the fact that k determines essentially what happens to the flow, this multiplier, and there are 3 possible cases, so or 4 possible cases. First case is when minus 2 less than t is less than plus 2. So t is real A, B, C, D are complex constants in general, but if A plus D is real and it lies between -2 and +2, then it is clear that this K has unit modulus, because it is of the form A minus IB over A plus IB, where A and B are real numbers, and the modulus of each of these is the same, square root of A squared plus B squared. So this immediately implies K mod K equal to 1 in this case. K itself is not equal to 1 because this thing is not 0 out here, it is strictly between -2 and +2. So mod K equal to 1, K not equal to 1. Only in modulus is this number equal to 1, but it is not unity itself. And then you have what is called an elliptic transformation. The second case is when t equal to plus or minus 2, real and plus or minus 2. Now the two fixed points coincide and k equal to 1. This transformation is called a parabolic transformation. The third case is when t real mod t greater than 2. So it is on the real axis A plus D, but outside -2, the interval -2 to +2. What happens then? Then this is a number, this number is certainly a fraction of some kind, it is a real number of some kind. So mod k is a real number and is not equal to unity. And this thing is called a hyperbolic transformation. These words come from, well, it is not hard to see where they come from. They actually come from the nature of the flow around the fixed points in the complex plane or on the Riemann sphere. And the fourth case is T complex. T not an element of -2. So it is not on the real axis, it is some complex number, and then this thing here is called a loxodromic okay. This is a special case of the loxodromic transformation when the imaginary part of t k vanishes, of t vanishes and it sits on the real axis, but not in the interval -2 to +2. Okay. So using this is the starting point of the actual classification, independent of the fixed points. There are some cases where you can see k equal to 1, the two fixed points coincide and so on and so forth, but other than that, that is a normal useful for normal form, but this is useful for analyzing the flow, the actual flow in the complex plane. So I will not go further into this because there is a whole lot that you can do, except that I introduced the concept of the isometric circle and pointed out that a certain circle mod Cz plus D in this case equal to 0. This circle mod Cz plus, what was the isometric circle here, mod so let me write this down separately. So mod Cz plus D equal to 1 was the isometric circle. The reason we called it the isometric circle was because lengths on this circle do not get changed, they do not get stretched or contracted under the mapping. This circle is mapped just as we know that every circle is mapped onto some other circle in a Möbius transformation. This circle is mapped onto some other circle. It is actually mapped onto the isometric circle of the inverse transformation. That is a simple exercise to prove. And what was the inverse transformation to this? The W equal to this thing immediately implied that Z was equal to dz minus B over minus Cz plus A. Okay. Again AD minus BC is equal to 1 still. Pardon me? W, sorry, I used a different symbol, so it should be W. So this is mapped onto, this circle is mapped under the transformation to the circle minus CW plus A mod equal to 1. You should not make the mistake of assuming that the center of this circle is mapped to the center of this. Where is the center of this circle mapped to?
Minus D.
At infinity. It is mapped to infinity because you put Z equal to minus D over C, W becomes infinite, right. So the center of this circle is mapped onto infinity. Where is the center of this circle mapped onto in the inverse map? Infinity once again, right. So the infinity in the Z plane is mapped to the point A over C in the W plane, and minus D over C in the Z plane is mapped to infinity in the W plane. But this circle is mapped onto this, and what happens is in the Jacobian of this transformation dW over dz, this thing here is proportional to 1 over Cz plus d to the power 4. So what happens is that if this is less than 1, which is the interior of this circle, then under the mapping lengths expand. So the inside of this circle is mapped onto the exterior of this circle and vice versa. Okay. But on this circle lengths do not change, they do not stretch at all, they remain unchanged. And a lot of further information about Möbius transformations makes use of this isometric circle, the idea of the isometric circle. We are not going to do very much more with it, but I will try to give some exercises based on this thing. Okay. Now the next thing we said was that these transformations form a group, and that is very easy to see once you have the normal form, because it is clear iteration just keeps multiplying this and you still have again more and more Möbius transformations. Once again the composition of any two is again a Möbius transformation. Every transformation has an inverse, they are all invertible because the determinant is equal to 1 and so on. So they form a group, but the group is not the group of, so this group, the Möbius transformations on the complex numbers, is isomorphic not to the group 2C, which is the group of unimodular, that is determinant 1, 2 by 2 matrices with complex entries. It is not quite that group, but it is this group quotiented with the cyclic group of order 2, because we know that this transformation does not change if A, B, C, D all of them change sign. So there are 2 matrices in SL2C which correspond to the same transformation, and they differ only by a sign. That is taken into account by saying that this is modulo Z2, so up to a sign. This is a 2-to-1 homomorphism between SL2C and this group, the Möbius group here. Now it turns out this group has other interesting properties. This group is also what is called the universal covering group for the homogeneous Lorentz group in 3+1 space-time dimensions, and that group is also got a parameter space which is doubly connected. So once again SL2C over Z2 is isomorphic to the homogeneous Lorentz group, so this is also isomorphic to SO3, 1. Therefore there is a 1-to-1 correspondence between the group of projective transformations of a complex variable or Möbius transformations and the group of homogeneous Lorentz transformations in 3+1 dimensional space-time, which can be exploited. but we are not going to go into that here, but that is a sort of mathematical relationship which is extremely useful. Okay. So this is the general Möbius group, but we could ask the question, are there any subgroups of this group, which namely subset of transformations which themselves form a group among themselves, and the answer is yes. This set of transformations, so let us write that down. The set of transformations A W equal to AZ plus B over CZ plus D, A B C D real, and AD minus BC equal to 1. This set of transformations also forms a group. Okay. So it is interesting that even though Z is a complex number variable and W is a complex variable, this combination here where A, B, C, D are real, you multiply 2 such real matrices, you get one more real matrix and so on. So they too form a group among themselves. Once again you can change the sign of A, B, C, D and the transformation will not change. So this subgroup is called the Möbius group on the reals, and this is isomorphic to the special linear group on the reals quotiented with Z2. By the way, there is a fancy name for this thing here. This guy here is called the projective special linear group 2C. It is written in this fashion to show that it is up to a sign. Those both matrices are projected onto the same entity. So this is also equal to P S L 2, R, a more compact way of writing the same thing. Are there any other groups of this kind? Well, interestingly enough, yes. It turns out, and it is not hard to verify, that if A, B, C, D are integers, then they form a group among themselves too. So you restrict A, B, C, D to integers, and that forms a group in itself. This group has a very important role to play in mathematics. This is called the modular group. So we have identified several of them. There is one of them is this, real, and then the second one is where these fellows are integers. This fashion. Similarly, you could have A, B, C, D of the form of what are called Gaussian integers, namely they are of the form m plus ni mn integers. These are called Gaussian integers, right, where you have a complex number in which the real part and the imaginary part are both integers. They too form a group. So all transformations in which A, B, C, D are restricted to Gaussian integers, they form a group among themselves. There are several other very interesting groups, for instance subgroups. For instance, you have one which is the group, the subgroup, the group, the invariance of the unit circle. In other words, you ask the question, what is that set of Möbius transformations which takes mod Z equal to 1 to mod W equal to 1. So under the map you want mod Z equal to 1 should map on to mod W equal to 1. So the unit circle in the Z plane should map on to the unit circle in the W plane. or on the Riemann sphere the equator should map to the equator in this case. Well, it requires a little bit of work to show that this actually is a group by itself. What you have to do is to say, alright, Z goes to AZ plus B over CZ plus D. So you impose this condition given that mod Z equal to 1 and ask what is the condition on the coefficients A, B, C, D such that mod W is also equal to 1 under this map. And then you discover after a little bit of work, and I have left this as an exercise, you discover that this will imply that the matrix A, B, C, D must be of the form either A, B, B star, A star, with mod A squared minus mod B squared equal to 1. You want the determinant always to be equal to 1. So it should be of this form. Then you are guaranteed, once this condition is satisfied, that mod Z equal to 1 is mapped to mod W equal to 1. Or, so let us call this one set of matrices, or it should be of the form A, B minus B star minus A star with minus mod A squared plus mod B squared equal to 1. Okay. So both these are permitted. And once again you can change the sign of A, B, C, D completely, all 4 coefficients, and the transformation will not change at all. But the set of matrices, 2 by 2 matrices which satisfy this condition or this condition is of interest in itself. It is very closely linked to the set of matrices which give you the unitary matrices, 2 by 2 unitary matrices. Does anyone know what is the most general form of a 2 by 2 matrix which is unitary? So you want to start with a matrix alpha, beta, gamma, delta, and let us call this matrix U, and U dagger therefore is alpha star, delta star, gamma star and beta star in this fashion, and now impose U dagger equal to I. So multiply the 2 and say it must be the unitary matrix, that is a unitary matrix. Now this is going to give you conditions on these coefficients, and you can find out what is the most general form of a 2 by 2 matrix which is unitary. I will leave this to you as an exercise. We are going to come back to this because it is a very important piece of information. You should be able to write down the most general 2 by 2 unitary matrix. After that we will impose the condition that the determinant should also be equal to 1. By the way, this will imply that U is that this matrix, let me just call it M for the moment. This will imply that M is an element of the group U2, namely the group of 2 by 2 matrices with complex entries which are unitary. They form a group among themselves and it is called the unitary group, the U2, denoted by U2. So I want you to find the most general form of this U2. Incidentally, how many parameters are sitting here? There are 8 parameters, 8 real parameters, because each of these numbers is a complex number in general. There are 8 parameters, and when I say something is unitary and I impose this condition, I compute this matrix and I equate it to the unit matrix. So there are 4 conditions on the 4 elements. So there are 8 parameters and there are 4 conditions among them. So how many independent parameters would you expect? 4 independent parameters. So I want you to find those parameters. So it is clear these fellows cannot all be independent of each other. You could choose alpha and beta to be independent, and then you must show that gamma and delta is determined by it or some such thing. But try this out. Now further impose determinant m equal to +1. When you do that, you have not only imposed the condition of unitarity, but you have also said the determinant is equal to 1, and now you get a further condition. By the way, what is the determinant of this matrix? What does this tell you about the determinant of M?
Plus or minus 1.
What does it tell you? This is very important. What does it tell you about, what does this condition tell you about the determinant of M? Yeah, it says modulus determinant M equal to 1. It says modulus. But these are complex entries. So what does it say about determinant M? It is a pure phase factor. Where theta is real. So you should not be fooled into saying this immediately implies that determinant M is +1 or -1. No, just says it is a phase factor. Could be +1, could be -1, but it is a phase factor. So that is needed in order to derive what are the conditions that you have here. Remember this condition. Now if you further impose determinant M as +1, that means theta must be equal to 0. Now how many parameters do you think there are? There are 3 independent parameters, because you have got 4 conditions on the elements and then you have got determinant equal to 1. So there are 3 independent parameters, and this would imply that M is an element of the special unitary group in 2 dimensions SU2. As you know, SU2 plays a fundamental role in quantum mechanics in spin, especially in spin half, and it is fundamental to physics in that sense. We will say a little more about this. Now the question is, what is the most general matrix in SU2? It turns out the most general element in M must be of the form alpha, beta, beta star, alpha star with a minus sign. And the determinant must be 1, of course, so mod alpha squared plus mod beta squared equal to 1. The most general unitary unimodular matrix you can write down, 2 by 2 matrix, involves 2 arbitrary complex numbers satisfying the condition that the square of their moduli add up to 1. Okay. So how many independent parameters are there? 3 independent parameters, because if you call alpha 1 and alpha 2 the real and imaginary parts of alpha, and similarly for beta, then this says alpha 1 squared plus alpha 2 squared plus beta 1 squared plus beta 2 squared is 1, which means one of them is determined by the other, by all the others. Okay. What kind of parameter space is this? No, not S2.
It's 3-dimensional sphere.
It is not S2, because what you have, the parameter space, and we will pay attention to the parameter spaces of various groups. I will come back to this when we talk about rotation groups. You have alpha 1 squared plus alpha 2 squared plus beta 1 squared plus squared equal to 1. It is a 4-dimensional space. Alpha 1, alpha 2, beta 1, beta 2 are 4 real numbers, so they live in R4, but then they satisfy this constraint. This is the surface of a hypersphere in 4 dimensions. It is a 3-dimensional object, and this is S3, the 3 sphere. What is the 1 sphere? It is just a circle. It is a 1-dimensional object, it is just topologically equivalent to a circle. The 2 sphere is a familiar surface of the globe that you are used in, but it is a 2-dimensional object, so mathematicians write S2. The fact that it is embedded in 3 Euclidean dimensions is incidental. It is a 2-dimensional surface. This is S3. We can't conceive of this. This is like taking 3-dimensional space and putting all the points at infinity in one point, sort of sewing it together. You can do that for a pancake, but doing it in 3 dimensions for 3-dimensional space is not so trivial. And whatever it is, this is the parameter space of SU2. It happens to be simply connected in the sense that you can go from any point to any other point on the space continuously arcwise without leaving the space. So it is connected, and it is simply connected in the sense that every closed path on this space can be shrunk to a point, distorted to a point without ever leaving the space. Okay. So a space where every closed path can be completely shrunk to a point is called a simply connected space. Okay. Is S2 simply connected?
Yes.
Yes. On the surface of this globe I can put a rubber band and you can shrink it without leaving the space, certainly. Is S1 simply connected?
No.
What do you think?
No.
No, S1 is not, because it is clear that this is S1 and you can't leave the space. So any closed path would mean you start at some point, you go there and you come back. That is a closed path, and you can certainly shrink it to a point. You could go all the way around, not quite meet the first point and come back, and you can still shrink it to a point. But the moment you go all the way around here and come back to the starting point, it is like fitting a rubber band on the rim of your cycle wheel, and then short of cutting it there is no way in which you can shrink it to a point. Okay. So that is a path which cannot be shrunk to a point. Now you can do that twice, and that can never be changed to a path which goes around once. So you have another path which is distinct from those which you can shrink to a point and those which go around once, and then you can do it 3 times, 4 times, and you can do it in the opposite direction, -1 times, -2 times, and so on. So each time, depending on how many times you go around this space in the positive sense or the negative sense, you have a winding number associated with each such path, and all these paths can be classified into equivalence classes which are labeled by this winding number. So 2 paths which can be deformed into each other belong to the same class, and they would correspond to the same winding number. Now the set of these winding numbers themselves forms a group under addition. The integers, they form a group under addition. So the technical way of saying it is that the fundamental homotopy group, namely the group of equivalence classes of closed paths on this space of S1, happens to be the set of integers, the group of integers under addition. And it is written in a sort of evocative fashion. It is written as pi1 of S1 is isomorphic to the set of integers. Okay. This has a role to play, and we will talk about this a little later. But S3 is simply connected. So what one says is pi1 of S3 is a trivial group. In other words, it has only one element. Every path can be shrunk to a point, so there is only one equivalence class. When you have a group with one element, it is called a trivial group, and mathematicians like to write it as just 0. This is just a notation. It says there is only one element in a group. Okay. So this space is simply connected, the parameter space of SU2, which is going to play a very, very fundamental role. Let me make a statement here that whenever I talk about a covering group of a certain group, like in the case of the Möbius transformation, I said SL2C was a covering group, and modulo Z2 you got the Möbius group. That SL2C is a simply connected group. Okay. So the covering group is simply connected always, and that has consequences too. We will get back to this. Now the question is, what are these things? This is not quite the same as that. There is a slight difference here between this sort of thing and that kind of matrix there, because here we had alpha beta minus beta star alpha star, and you had mod alpha squared plus mod beta squared equal to 1. On the other hand, here you got A star, B star with mod A squared minus mod B squared equal to 1. So you see that little minus sign here has immediately changed everything completely. What is the parameter space there? What is that equal to? What's this? What does this tell you? This sort of tells you that A1 squared plus A2 squared minus B1 squared minus B2 squared equal to 1. What kind of object is that? It is not S3, that is very clear because there are minus signs there. What kind of object would that be? It is a hyperboloid, it is a hyperboloid, right. You know that x squared plus y squared equal to 1 is a circle, but x squared minus y squared equal to 1 is a hyperbola, 2 branches of a hyperbola. So if you had on the plane, if you had x squared minus y squared equal to 1 and you plotted x here and y here, it is these two fellows here. What if you had y squared minus x squared equal to 1? It is of course these two fellows out here, right. And the big difference between a hyperbola and a circle is that a circle is compact every point and it is bounded, but a hyperbola goes off to infinity. So these things, these parameter spaces are unbounded. They can become arbitrarily large because you can make A2 very large and B1 very large and still have the difference very finite here. So these are non-compact, these parameter spaces, the groups are said to be non-compact, whereas the group here is compact and plays a very, very significant role here. Now this group here is the group, this set of matrices, they form the group SU1 comma 1 because of that minus sign. So it is the set of matrices which do not satisfy a unitarity condition, but which satisfy a condition like mg m dagger equal to G, and G is this metric matrix minus 1. So I leave you to verify that the most general 2 by 2 matrix which satisfies this condition with this matrix G here is either of this form or of this form. It has got to be one of these two. These are like two different parts of the hyperbola, as you can see. One of them corresponds to something like this and the other corresponds to something like that, but they are non-compact. These spaces are non-compact, and this is called an indefinite unitary group. The reason is that this thing here can change sign, this quantity can change sign. So not all the terms do not appear with the same plus sign, but there is a minus sign in between, and that makes it non-compact. Okay. This group SU11, oh by the way, the group we are talking about of Möbius transformations of course is not SU11 itself, because as you know, for every SU11 matrix you can change the signs of all the terms and you would have still the same Möbius transformation, right. So again you have that modulo Z2 business, but the group that's of the matrix group that's of interest here for these Möbius Möbius transformations which leave the unit circle invariant, they are related to SU11, this group SU1. Now SU11 itself has other interesting properties. This group happens to be isomorphic, interestingly, to SL2 comma R. So the set of 2 by 2 matrices with unit determinant with real entries is in 1-to-1 correspondence with those matrices of that kind, and it is also isomorphic to the group of canonical transformations with 1 degree of freedom. So all matrices which satisfy a certain symplectic condition. So this contains all 2 by 2 matrices with real entries such that m omega m transpose equal to m, where this matrix omega is 0 1 minus 1 0. These are called symplectic matrices, and I will talk a little bit more about it when we do group theory, because all the canonical transformations of a system with n degrees of freedom, Hamiltonian system, will form a group called the symplectic group SPn 2n comma r, okay. And of that this is the case n equal to 1, and it so happens that when n equal to 1 you have all these wonderful relations, they are all isomorphic to each other. So again exercise for you, which is to show that the group of the unit circle, the group that leaves the unit circle invariant, would contain matrices of this kind or this kind, and nothing else is possible, and further that the most general matrix which satisfies this condition is again the same thing, okay. So it is just a piece of algebra which you have to do, but I would suggest you do this first, because this will tell you how to go about it in the most general case. Okay. Are there any other subgroups? Well, there are lots of other subgroups, but here is an interesting one. This is called the group of cross ratios. I am not sure if it has got other names. So how many had we done? We had done about 3 or 4, so this is probably 4. Or the fifth one? Was it the fifth one? Okay. Oh yes, we had the Gaussian integers too. Which is the following. Suppose z goes to 1 over z. That is an inversion, right? Z goes to 1 minus z. What kind of transformation is this? Well, it says about the point z equal to half, you rotate by pi, and z goes to 1 minus z. And the point half remains invariant, as you can see. So it is a rotation about half, but since you are also changing z to minus z, there is a minus sign there, it is a rotation by pi. So this is an inversion, and this is a rotation. Well, you combine these and you can have z goes to 1 minus 1 over z. Right. So you first invert and then you rotate. You could do the other thing. So you could rotate and invert. Z goes to invert. What else could you do? You could do z goes to, so after you do this, so you rotate, invert, you rotate again, and then you get 1 minus this stuff, and what will that do? So that will give you z, and the minus 1 will cancel, so that is going to become z goes to z over z minus 1. Right. So this says rotate, invert, rotate. You could do the other way. You could invert, rotate, invert. Now what will that do? Well, if you invert you get this, you rotate you get this, and then you invert you get back to that guy. So that is not doing anything new. You could also just as well have written this as invert, rotate, invert. Okay. And of course to show something as a group you need the identity element. So z goes to z, this is the identity. Identity transformation. Now it is not hard to verify that these form a group by themselves, and they are Möbius transformations, special cases. So for instance, in this case B is, if you compare it with what happens to AZ plus B over CZ plus D, it is clear that in this case you have set, well here ABCD is trivial in this case, nothing happens except that all this is 0, that is equal to this, they cancel and go to 0, etc. So what is the identity correspond to? It says C is 0 and then A over D is 1, B over D is 1, and we put AD minus BC also equal to 1. So that is a trivial case, but here this would mean that A is 0 and D is 0 in this case, and so on for every one of these transformations. but it is a trivial thing to check that they form a group among themselves. This is a finite order group, there are 6 elements. So you should write down for these 6 elements the group multiplication table. The composition of 2 more will give you 1 more, etc. So I would like you to write this down. Is this an abelian group? Do these fellows commute with each other? Certainly not. You can see that they produce different results if you do it in different orders. So it is not an abelian group, it is not altogether a trivial group. It is a group of order 6, it has a lot of interesting properties, etc. And it is called the group of cross ratios for a reason I want you to discover by playing with these things here. Remember, under a Möbius transformation, cross ratios do not change, they remain unaltered. So there is a simple reason why this is called the group of cross ratios, and I want you to discover this. Okay. Well, there are several other properties of these transformations, but we will leave that to the, I will leave that to the exercises so that you get some practice understanding this, and then if necessary we will come back and discuss those properties once again. But let me summarize finally by saying what is the significance of these transformations. Möbius transformations are the most general possible transformations which are one-to-one maps of the Riemann sphere to the Riemann sphere. They are invertible, they are one-to-one, that is the most general form. If you did this keeping the point at infinity fixed, then you just get linear transformations. But the moment you allow the point at infinity to map to some other point, you get this interesting group of transformations. And because it has got all these connections with these other groups and so on, it is of very great interest in many contexts. Okay. And because it is a mapping by an analytic function, it is conformal. Circles are mapped into circles under this transformation. There is a certain circle which is not stretched or contracted, and then there are various possibilities for stretching fixed points and the flow around these points and so on and so forth. So those are some of the interesting properties of these transformations. Okay. Now one point which I forgot to make about the invariance group of the unit circle is that a transformation of the form A, B, B star, A star, as opposed to a transformation of the form AB minus B star minus A star is the following. Under both these transformations, remember that mod Z equal to 1 is mapped onto mod W equal to 1. But you could ask, what is the main difference between these two transformations? They are like two parts of the hyperbola, two different branches, right? Under this transformation, points inside the unit circle in Z are mapped to points inside the unit circle in W, and those outside are mapped to those outside. Okay. That is something else you can verify easily. On the other hand, under this set of transformations, points inside the unit circle here, mod Z less than 1, are mapped to mod W greater than 1 outside the unit circle, and vice versa. So that is the difference between this set of matrices and this set of matrices. There are two disjoint sets of matrices. Together they constitute the SU11 group. Okay. And when you, in terms of Möbius transformations, this property of mapping the unit circle to itself, keeping the interior unchanged, is restricted to one of this, and exchanging the interior and exterior is in this set of transformations. These are all easily verified, and you should do so right now. The algebra is quite simple. So once you show that this is the most general form of a matrix which satisfies this condition, then it is easy to come across to derive these conclusions as well.